this video, I'm going to explain what a chi-squared test is and how you can interpret a graph for a chi-squared test. So I think it'd be a good idea to first start off by kind of discussing what exactly a chi-squared test is supposed to do. And so essentially what the chi-squared test does is it's a test to compare the observed frequency of the results with the frequency that you expect. So, in terms of genetics, the most common example is, let's say you mate two heterozygotes and you get a certain number of offspring. And so you know from previous experience that you expect a 3-to-1 ratio of the dominant phenotype to the recessive phenotype. And this is because you crossed a heterozygote. So it's the 3-to-1 ratio when crossing two heterozygotes. So then now let's say you get a certain number of offspring and you want to know if the number of offspring actually fits the ratio. So you want to know if it's the expected result. So in real life, you're not always going to get, like, let's say you have 4 offspring, you're not always going to get 3 dominant phenotypes and 1 recessive phenotype. So let's say you have 100 offspring and you have maybe 73 dominant phenotypes and then you have 27 recessive phenotypes. So it's pretty close to the 3-to-1 ratio. So now we're going to use statistics to actually determine if it fits the 3-to-1 ratio. And so that's essentially the purpose of the chi-squared test. And so if the results are way off, that could imply that there's something else at play, another genetic factor at play. And so now let's take a little bit of a look at this graph. So here you see all of these purple lines, and then degrees of freedom on there. So we'll talk about that in a minute. And the x-axis is the x squared value. And then notice it's a little weird. It goes from low to high. And then on the y-axis is the p-value. And so as you can see up here, I've just given us some numbers to work with just to make it a little simpler. So first, let's try and find out the x squared value. And so as you can see, you have the equation up here. The x squared value equals the sum of the observed value minus the expected value squared over the expected value. And so as you can see here, so we have to find the sum of this value for the for the dominant phenotype and add it to the value of the recessive phenotype. So what does this mean? All right, so our observed value for the dominant phenotype is 300. So then our expected value is 75, or 3/4 of the total value. So you could do that by adding 300 to 110 and then multiplying by 0.75. So I did the math out, and our expected value of the dominant phenotype is 307.5. So then you have the 300 here minus the 307.5, which is the expected value. So the 300 is observed value, the 307.5 is the expected value, and you square that and divide it by the expected value. So now we have the dominant phenotype, and now we have to calculate the recessive phenotype and add them together. So I just calculated the x squared value here for our dominant phenotype. So now let's do the recessive phenotype. So I went ahead and just calculated the expected value by multiplying 0.25 by the total 410, and I got 102.5. So then we find the difference between the observed value, which is 110, and the expected value, which is 102.5, square that and divide it by 102.5. So I went ahead and did the calculation out, and we get 0.18 plus 0.51. So our total x squared value is 0.69. So then, as you can see on this graph, that value lies somewhere around here on this line over here. So then the next step that we need to do is determine the degrees of freedom, and this one's pretty easy. So most of the time in genetics, the degrees of freedom is simply the number of classes minus 1. So in this case, the classes are the different types of phenotypes. And so the degrees of freedom would be two phenotypes minus 1. So the degrees of freedom is 1. So we would use this slope right here. And then, so now we just match it up. So our value was about 0.7, let's say, and so that's around here. And so that matches up to right about that point. And then, so now you have to look at the p-values. So a p-value that is going to be really small, and such as the values here in red. Usually if you have a p-value that is less than 0.05, that means the results are statistically significant. So they're pretty different than what you expected. So ours is up here. So let's say it's about 0.6. And so that means if essentially at this point all you need to really know is that if it's in the blue over here, that means it didn't differ from the expected value. So the values you got were within the range of what was expected. And so that pretty much sums it up for this video. I hope you liked it and found it useful. If you did, please be sure to give it a like and subscribe if you want to see more videos like this.